Hello, and welcome to the video. In this video, we will be going over the solution to problem 9 on midterm 3. Problem 9 asks us to consider a particle under the influence of a potential under a potential equal to beta over r to the k, where k is a varying integer. We want to find the resultant radius r null, of the circular orbits underneath this potential, and we want to also consider the frequency of oscillations about this circular orbits whenever the particle is given a tiny perturbation. We are then asked to find a few integers k such that underneath the corresponding potential, the perturbed orbit that we derived from B is closed. The first part of the problem is very simple. We know our potential. We can find our resultant force by taking the negative derivative of that. We know that our orbit is circular, so we need to have the magnitude of the radial seeking force to be equal to the centripetal force. This gives us this equation, and when we make the substitution of the angular velocity in terms of instead the angular momentum, and then rearrange for all r, we get this expression right here, which is our answer. Note, we should note that since this is a circular orbit, that means the radius stays constant, which means that under these conditions at this radius, this position is a stable equilibrium for our system. Now we address part B and part C of our problem. To do so, we introduce a quantity of effective potential, which is this expression right here. For now, just take it for granted that this is a more accurate measurement of the energy for our object than just the potential by itself. Now we want to perform a Taylor series expansion for our effective potential around r equals to r naught, which gives us this right here. For now, we'll only consider terms up to the quadratic term, as higher order terms will be negligible. We can note that since r0 is an equilibrium, that means that the first derivative of the effective potential at r0 is going to be 0 because of characteristics of an equilibrium. You can mathematically verify this yourself. You just take the first derivative of the effective potential and then plug in r equals to r0, which we found previously. You'll find that it does indeed equal to 0. And the constant term, well, we can just choose our reference points such that the effective potential is just equal to 0 at r equals to r0. This leaves us with only the quadratic term being non-zero for our effective potential. We now make the substitution that epsilon equals r minus r naught. This epsilon represents our small perturbation around our circular orbits. Noting then that, again, just the force is equal to the negative of the derivative of the effective potential with respect to epsilon, we get this equation right here. When this left side term is the force, and this right side term is the negative derivative of the effective potential. We can then rearrange this into a very familiar equation. This is just harmonic oscillation. And we know that the coefficients for the zeroth order variable is just the square of the frequency of our oscillation. And so indeed, in order to find the frequency of oscillation for our small perturbation, we need to find this quantity right here. Finding this expression is very easy. You just need to take the second derivative of the effective potential, and then plug in r equals to r naught, and then take that expression and then substitute that back in for our expression for our frequency, which gives you this expression right here. If you further substitute r naught for the complete expression that we found in part A, you get this expression right here as well. We next find the frequency of the orbit itself, which is very simple. We take the same equation for part A. Instead of solving for r, we solve for omega, which gives us this expression. Therefore, the ratio of our frequencies is given by this. Substituting r for its complete expression, we get this expression right here. And when this expression is equal to a rational number, we have that the perturbed orbits will be closed. This happens when k equals to 1, k equals to -1, k equals to -6. And these are just some examples. There are an infinite number of k's such that the orbit is closed. In this case, when k equals to 1, we have that the ratio is 1, which just means that the particle will oscillate one time in one orbit. When k equals to -1, the ratio is 2, which means that the particle will oscillate twice in one orbit. And when k equals to -6, the ratio is 3, which means that the particle will oscillate 3 times in one orbit. And all the graphs for each orbit is visualized below right here.